Hello. In this session, I'm going to um, work some problems in review for the midterm test. Um, there will be one problem from each chapter, so there are 6 chapters, 1 through 6, and problems from chapters 1 and 2 will be 10 points each. They'll be shorter problems, and the problems from chapters 3 through 6 will be 20 points each, so they will add up to 100. You can bring a um, calculator. You can bring your cell phone in airplane mode and use the um, engineering economics career app. That's what I always use when I work problems. You can use Excel, and you can bring 2 sheets of paper with anything you want written on the front side. Um, and I will provide additional information about the test taking procedure um, in module 6.5, which is where the test will be. So um, I'll get right into working problems. I always go through the same process that you would work statics or circuits or any kind of engineering problem. You read the problem, you look at what's given to you as information data, and in this case, you draw a cash flow diagram. I always recommend you do that, and then you apply the proper formulas to solve the problem. So um, the first problem, the one from chapter 1, says you borrowed $10,000 for 6 months at a simple interest rate of 10% per year. Uh, the only chapter we really deal with simple interest is in chapter 1 that I can recall. How much? So it says you borrowed some money. We'll draw the cash flow diagram after I read the whole question and try to understand that part, okay? So how much must be repaid to the lender at the end of 6 months? So you're going to keep this $10,000 and then repay interest and principal at the end of 6 months. So let's draw the cash flow diagram. Um, Cash flow to you will be, actually, I should put it the other way. Cash flow to you will be $10,000. And then if we think about this as 1 year, then at this point in time, 1/2 a year, we're going to have to pay back, so that'll be negative cash flow to you, both the principal plus the interest, and we'll call that the future value. And the formula for the future value at simple interest, that's this I for simple interest is equal to PIN, the principal times the simple interest rate times the number of periods. Okay, so this is what $10,000 times the rate, which is 10% per year, so that's 0.1, times the number of years, and that's a half, or 0.05. And if I multiply that through, I'll get 500. And then to get the future value, then F is equal to the original principal, which is 10,000, plus the interest, which is 500, which is $10,500, and that's the answer to question 1. I'm going to work a quick problem in chapter 2 now, and then we'll go on to the tougher chapters, I guess, beyond there. A manufacturer is did I start this up? Investigating whether it should update in place equipment now or wait and do it later. So this is whether you spend some money now or you spend it later. If cost is $200,000 now, what will the equivalent amount 3 years from now at an interest rate of 10% per year? So we're given basically, we could either spend $200,000 now, or we can wait and spend some future value. And it's asking you how much is that value, and the number of periods is 3 years, 1, 2, 3, and these are years, and the rate is 10% per year. And if it doesn't state what period, then we assume compounded annually. So now we just want the present value of a future sum, which is F is equal to P. Find F given P at rate I for period N. This is the generic symbolic formula. I seldom use the algebraic formulas because I'm going to use the app, the Engineering Economics Career app, and I don't need the formula to use that. So I will have $20,000, and I'm going to use that as a plus number because I want to enter the answer as a plus number. And then times F given P, 10% per year for 3 years. And if you go into the Engineering Economics Career app, which I'll do now, and I want to go to the future value of a present sum, which is the first one at the very top, and the interest rate is 10%, and the number of periods is 3, and the present worth is 200,000. And I'm gonna press calculate, and it gives me $266,200. So that's the answer. And the next thing we'll do is go on to question number 3. By the way, on the test, just like on the homework, if you get an answer plus or minus 2%, you'll get it correct. However, on the test, you're also going to submit your work, and I'm going to grade that. And usually, almost always, it helps the student score higher, because if you get the answer wrong because of a little math error somewhere along the way, then I'm going to give you most of the credit for the problem, even though the answer was incorrect. Conversely, if you get the correct answer and the computer and Blackboard gives you full credit for the question, I'm going to still look at your work and see that you actually did the problem correctly, and you didn't just guess at the right answer or work it incorrectly and still get within 2%. So anyway, that's just on the grading front, so to speak. The next thing I'm going to do is work problem number 3. Another problem for you. This problem statement says investments of $3,000 per month are made into account for 2.5 years. Now, right away, we've got something that's a monthly series, and we're told it's there for 2.5 years, being done for 2.5 years. So that's 30 months. We can convert that pretty easily. But then as we read on, what is the future worth of the account after 2.5 years at an interest rate of 6% per year? So now we've got a per year thing, but it's compounded quarterly. Well, we almost always want to work with the period of the compounding. And in chapter 3, the author talks about what happens if your payment period is less than your compounding period, what happens if your payment period is greater than your compounding period, and so on. So we're going to basically note that we have a monthly equals $3,000. The number of months equals 30. How did I get that? Well, 2.5 years is 30 months. But the interest rate compounding, I, is 6% per year compounded quarterly. So what we realize now is that our payment period which the author designates PP, is less than the compounding period. He calls CP. In that case, we have to move the payments. So let's draw the cash flow diagram. We have investments, that's negative cash flows of $3,000 a month. So let's just put month 1, month 2, month 3, and that's the end of quarter 1. So I'm interested in quarters here. Month 4, 5, 6, that's the end of quarter 2, and I'll go on. We'll go up here to say 24, month 24. What would that be if we divide 24? That would be quarter 8, right? And then 25, 26, 27. That would be quarter 9. And then we'll go to 28, 29, 30. That would be the end of quarter. All of these have $3,000. And that will be quarter 10. Now, the question is, what is the future? So what would all this stuff add up to? Well, when we have a payment period less than the compounding period and the cash flow is negative, the author says move the cash flows that occur during a period, during a quarter, to the end of the quarter before, because this is a compounding point, this is a compounding, this one, this one, this one, so on. So he says move these cash flows to the next compounding point. So I move this is 3,000, and then I'm going to add another 3,000 and another 3,000. When I move these over, I'm going to end up with 9,000 at the end of each quarter. Then when I move these on over, 4 comes over, 5 comes over, 6 is here. We do the same thing we did there. So we're going to end up with each of these quarterly cash flows of 9,000. So now the formula is F is equal to A, F slash A, I, N, and this is quarterly. This has to be the quarterly rate, and this has to be the number of quarters. So this is equal to 9,000, that's dollars per quarter. F given A, interest rate per quarter. Oh, I have to get the effective interest rate per quarter. And the number of quarters, we got that as 10, all right. So let's get this effective interest rate. The effective interest rate formula is I is equal to 1 plus R for that period quarterly over M, which is the number of times it's compounded in that period, to the M power minus 1. Well, it turns out that this is just 1 plus, well, what's R quarterly? Remember, this is an R annual. It's not the I annual because it's not compounded annually. So this is R annual, and to get R quarterly, we just divide it by 4. So this is going to be 1.5% or 0.015. It's compounded once in a quarter. That's the number of times it's compounded in that period of time. And then raise that to the 1 minus 1. Well, this 1 cancels with that. This is just 1.5% to the 1 power. And so that's just 1.5%. So now we're going to plug in 1.5% here. And then if we go and look that up in our app, we're going to get, well, I'll go ahead and get it. We're going to get F equals $96,324 from the app. I didn't show you the app yet, but so that's the answer to question number 3. The next question, or the next chapter, chapter 4, there will be a 20-point question, but I'm not going to work any questions from this chapter. I'm just going to go over some of the theory in the chapter that's critical to you. To get the present worth, when we're comparing 2 alternatives, that they must have the same life. Now, if the alternatives have different lives, then we must get the cash flow for the least common multiple of life. So if you had a cash flow with a 2-year life and you had a cash flow with a 3-year life, the least common multiple of lives would be 6 years, and you'd have to repeat the cash flow for the 2-year project 3 times, and you'd have to repeat the cash flow for the 2-year project 2 times, and then find the present worth, okay? You must be able to calculate the present worth of a bond, okay? To work this test, you need to know the formulas for a bond that are given in Chapter 4. Basically, the cash flow for a bond includes a price, which is a negative cash flow, then a series of dividends, which are positive cash flows. It's basically an A series, and a future value, which is usually the face value if you hold the bond to maturity. If you sell it before maturity, it'll be the market value of the bond at the time you sell it. And finally, the concept of capitalized cost is brought up in Chapter 4, and the capitalized cost is the present worth of an infinite A series. If you actually work with the formula P equals A, find P given A, I, and N, and you take the limit as N goes to infinity, that formula goes to 1 over I. So you just divide the A series, so this would be A times 1 over I. You just divide the amount of the A series by the interest rate, and that gives you the present worth of an infinite A series. So you need to know those facts and you need to know how to work problems in chapter 4. So the next problem I'm going to work is one from chapter 5. And we'll start by reading the problem carefully and drawing the cash flow diagram and understanding what we're given and what we're looking for. Assume you won a worldwide lottery. That'd be nice. That pays 5 million in year 0. Okay, so you get 5 million right now. So that's basically, let's look at that. You get 5 million now. Then let's assume that at the end of year 1, well, it says 5 million at the end of year 1, so you get another 5 million. It's a real good deal if you can swing it. And then it says you get 200,000 a year from years 5 through 10. So let's mark this off. This is year 2, year 3, year 4, year 5. I'm sorry, years 5 through 100, not 5 through 10. And then it says, assume that 100 years is as long as infinity. Actually, if you discount something 101 years, it's worth nothing. So it might as well be infinity. But anyway, you're going to get 200,000 at the end of year 5, and then another 200,000 at the end of year 6. And that's going to go on all the way to the end of year 100. But he says, assume that's equal to infinity. So this is a uniform infinite A series, okay, or an infinite A series. I'm going to solve this problem by first finding the present worth and then convert the present worth to an infinite A series, because the question asks, calculate the perpetual, what that means forever, equivalent annual worth for years 1 through infinity at an interest rate of 10%. So we're given I equals 10% per year, compounded, we assume annually. Okay, so let's get the present worth first. The present worth at time 0, in fact, okay, that's the present. So that's equal to 5 million plus, I have to bring this 5 million back to time 0. So that would be 5 million P given F, that's a single payment out there, 10% for 1 year. Now I have to bring this infinite series back to time 0. Well, we just saw in the last chapter, to get the present worth of an infinite series, you just divide it by the interest rate. Well, but that present worth will be 1 year before the series starts, so that will be here at time 4. Then I'll have to take it from time 4 all the way back to time 0. So I'm going to take 200,000, divide it by I. That gives me the present worth at time 4, and then go P given F, 10% for 4 years. This is going to be the total present worth of the entire cash flow. If I work out some numbers here, I'm going to get P equals 5 million plus this function is going to give me 4,545,455. And then this is going to be 2 million, right? When I divide 200,000 by 10% or 0.1, it's going to give me 2 million. Then I'm going to take 2 million back to the present. And when you do that, well, I'll just put the 2 million here. 2 million. P given F, 10 and 4. And if you do that, first we'll add these two together. That's going to be 9,545,455. And then I'll get the present worth of this quantity here. This is 2 million P given F, 10% for 4 years. And that's going to give me, let's see, I don't have the exact value for that. Let's go ahead and get it since we're going to do that. P given F, that's P given A, that's not what I want. P given F, 10% is the interest rate. The number of years is 4, and the future worth relative to time 0, which was a present worth, is 2 million. And so I tell it to calculate, and I get 1,366,026 and $27 actually. And so when I add those two together, I get $10,911,000 and $482. Okay, $911,000 and $482. Now I'm going to take that p-value and convert it to an infinite A series. So A infinite for n equal infinity will be equal to P times I. It's the opposite of this one. This was A over I equals P. Multiply through that, you get A equals P times I. And so now I'm going to take this 10 million and multiply it times 0.1, which will give me 1,911,000. I'm sorry, that's not going to be right. I'm just moving the decimal place over. 1,091,148. And that's the final answer for this question. Number 5. So the next thing I'm going to do is work problem number 6 for you, and that will end the review for the test. And problem number 6 is one of the longer problems in the test, because this chapter involves rate of return. There's Excel functions that'll work rate of return, but only if you have a specified kind of cash flow. So you should learn how to do a rate of return questions both with Excel and by trial and error. I'm going to solve this one by trial and error because I think that's the more difficult, time-consuming way. But if you want to save time, certain problems can be worked by Excel. And I don't think this is one of them that can be worked by Excel. I'm not sure. Nonetheless, I'm going to solve it by trial and error. A project took 10 years of planning and cost $4 million, which was spent equally at 400,000 a year for 10 years, for years 1 through 10. So let's look at the cash flow. You're going to spend 400,000 in years 1 through 10. 1, 2, 3, and so on up to year 10, like this. These are 400,000. So that's what we know so far. It resulted in profit estimated at 270,000 per year in years beginning in year 11 and continuing perpetually. Well, that means forever. So starting in year 11, you get plus 270,000, and then year 12 you get 270,000, and that goes on for infinity. So 270,000, you get this nice infinite A series. And it says, determine the rate of return. Well, rate of return, which we use the symbol I star, is the interest rate at which the present worth equals 0. So we just say present worth at I star equals 0. And since I'm going to solve this by trial and error, and I'm told it's between 5 and 10%, I'm going to start with present worth at 5%. Okay. At 5%, this would be equal to, well, this is a series of minus 400,000 for 10 years. So it's minus 400,000. That's P given A. 10, the rate is 5% per year for 10 years, okay? And then we have this 270,000 forever, but it starts at year 11. Now, when we find the present worth of an infinite A series, we get that by just dividing by I, and that number or that value is 1 year before the A series starts. So that would be at time 10. Then we'll have to take that back to time 0. So we'll have plus 270,000 times P given A, 5% for infinite. That takes this series back to here. And then we take that P given F, 5% for 10 years. Well, so I'm going to put this over here. P at 5% is equal to, and I get this number, which is minus 3,088,694. That's this value here. This divided by 0.05 is going to be 5,400,000. That's this quantity, 5,400,000. And then I multiply that by this, which is P given F, 5% for 10 years. And I won't set that equal 0 because that's not the I star, it's just a guess. So I'm saying try 5%. So when I try 5%, I get 5% is equal to this and this. Well, this turns out to be, this quantity here turns out to be 3,315,000. So this is minus 3,088,694 plus 3,315,132. And when we add these two together, we get only 226,000 $438. that number is greater than 0, so we need to try a higher rate um, to get to 0, because the higher the rate, the more these numbers over here are, the positive numbers are reduced. So now we're going to try 10%, because the author told me it's between those two. So it should be, this should be a negative value then at 10%. At 10%, the present worth of 400,000 P given a 10% for 10 years. Well, the higher the rate, the smaller the present worth is going to be. And it turns out that's minus 2,457,827 plus, and when I work all this out at 10%, now this divided by 0.1 is going to be 2,700,000. Divided by 0.05, it was 5.4 million. Now, P given F, 10% for 10 years. So this is going to shrink more as well. So this is going to be equal to minus 2,457,827 plus, and this turns out to be 1,040,967. And when I combine these two numbers, I get minus 1.4 million, 1,416,860. So now I have, this is less than 0. So at 5%, it's greater than 0. At 10%, it's less than 0. So now we've got it between 0, and this is where we do the linear interpolation. And the formula for that is I star equals the first number, 5%, plus the difference between these two percentages, 10% minus 5%, times this value here, 226,438, divided by this minus this. Well, this is a minus, so it's going to be actually plus 226,438 minus a minus 1,416,860. This is all in the denominator like that, okay? And let's see, this closes this parentheses, this closes this parentheses, and this closes that parentheses, okay? So now I'm going to have 5% plus, this is 5%, times this ratio, okay? Turns out that that ratio is pretty small, 0.69. Oh, I'm sorry, it's not 0.69. It's some number, I'm not sure what that ratio is. Well, let's work it. I don't want to work it. Let's see. Yeah, I can work it. This would be 226,438 divided by, this was 1,643,298. And so that ratio is so small, when I multiply it by 5%, I just get 0.69. So this could be 5% plus 0.69%, which is 5.69%. And that's the answer to the question number 6. And that's it. Thank you.